Good morning. We'll continue electrocyclic reactions today. It's the second lecture of electrocyclic reactions. In continuation with the first lecture, I'll repeat electrocyclic reactions are those reactions in which a acyclic polyene system having k pi electrons reorganizes its pi electrons in such a way that it creates a cyclic system having one pi bond less, that is k minus 2 pi electrons, and a new sigma bond is created. We've already discussed different examples and even the stereochemical mode of electrocyclic reactions. We'll continue with this thing now, considering the 4n plus 2 pi systems. When we say 4n plus 2 pi system where n is a positive integer starting from 1, that means the minimum system we are considering here is when the value of n is 1. That means this would be 4 plus 2, that is a 6 pi system. And the simplest example of 6 pi system should be a hexatrine. I'll talk about the electrocyclisation of hexatrine. What does it electrocyclize into? Remember, electrocyclic reactions are reversible reactions in nature. So when I draw a hexatrine molecule, I draw again this in a cissoid form, which is the more reactive of the two. How do we write the product? It is again simple. We move the arrows in such a way, either in clockwise or anti-clockwise direction, so that we show that the terminal p lobes of the polyene system, let's say this is 1, 2, 3, 4, 5 and 6, the terminal p lobes of the polyene system undergoes a sigma bonded overlap leading to the formation of a cyclic system. So there will be a one bond formation between 1 and 6, 5, 6 double bond goes to form the 1, 6 bond, 1, 2 double bond goes to 2 and 3, 3, 4 double bond goes to 4 and 5. Of course, this was a 6 pi electron system, this is a 4 pi electron system, and a new sigma bond is formed. Hence, these reactions are categorized as electrocyclic reactions. I'll now discuss an example in which I'll talk about the stereochemistry here. Let's say, for example, I am considering a hexatrine. Let me put it this way. Let's say 2Z, 4Z, 6E, octa 246 trine as my starting compound, and I want to consider the conrotatory ring closure of this one as well as the disrotatory ring closure of this one. But before I do that, I need to write this product. What is this product? It's an octa, that means the 8 carbon atom system with 3 triple bonds. So of course I'm considering the 3 triple bonds as the framework, that is the triene system as the framework. So when I draw a trine, I draw it like a hexatrine, like this. So this is my framework, right? 1, 2, 3. Now since it is an octa, that means it has 8 carbon atoms, there will be 2 more carbon atoms here, and I have to consider the geometry of this 2 carbon atom. The second double bond, that is this double bond, let's say, is having a Z geometry. That means this methyl would be somewhere here. This is hydrogen, this one was hydrogen. The 2 large groups are on the same side. That means this is first carbon atom. The second carbon atom's geometry would be Z. Fourth, 2 hydrogens are here. Of course, this double bond has 2 similar or larger groups on the same side. Therefore, again, the fourth double bond is Z. And as far as the sixth double bond is concerned, it has E geometrical isomerism. That means the 2 larger groups are supposed to be on the opposite side. Therefore, this is the shape of my starting compound, which I've referred here, in which the methyl on the second carbon atom is towards the left. The methyl on the 7th carbon is towards the left. Now I consider the conrotatory ring closure of this thing. Before I draw the stereochemistry of the product, so first of all I have to cyclize the system. The cyclization would again remain simple. This is how I move the arrows, and this is how I write the product. The only difference is this one was your second carbon atom, third, fourth, fifth, sixth, seventh. The only difference is that second and 7th carbon atom is now a stereocenter. That means this would have one group above the plane, one group below the plane, one above, and similarly one below. Now conrotatory closure can be in 2 possible methods. The lobe on the second carbon atom, the p lobe, the pz unhybridized lobe of the second carbon atom and the 7th carbon atom have to move, because it is a conrotatory closure, has to move in the same direction. Either both the lobes are moving in clockwise. Let's say first product which we'll write will show that both lobes are moving in a clockwise direction. And when we write the second product following the commutative ring closure, we'll try to write the product corresponding to the thing when both lobes are moving in an anti-clockwise direction. So I can have two possible products here. Let me first of all write the structure of the product. That will remain same. The only difference that will come in the two products is that both the products will have the different position of the substituents at second and seventh carbon atom. Okay, let's first of all consider the clockwise mode of closure. Second carbon atom, seventh carbon atom would have their p lobes like this and this. Let me put it this way. Okay, and the two thumbs are like this. Okay, consider it this way, that this second carbon atom's lobe is moving towards the in a clockwise direction. That means in the right side like this. When it moves towards the right side, where will it pick this methyl? It will pick it above like this. Since second lobe is moving, it will move like this and pick the methyl above. That means this methyl here will go above the plane and correspondingly hydrogen will go below the plane. And similarly, when this lobe has to move in a clockwise fashion, that means like this. Now this methyl is here. This will also move like this. That means this methyl will go above the plane. That means in this particular case, both methyls will go above the plane and both methyls in the product will have a cis geometrical relation with respect to one another. This is one product in which both the lobes are moving in a clockwise fashion. If both lobes are moving in an anti-clockwise fashion, second moving like this and similarly seventh moving like this. Now what will happen to the substituent here? The substituent on second is here. If it moves like this, the substituent goes down. If it seventh substituent is here, if it moves like this, the substituent goes down. That means in both cases the substituent methyl would go down and correspondingly hydrogen would go up. And again, as you can see, the geometry of the products again in this case is cis. So that is how we write the product of the hexatrine system or the 4n plus 2 pi systems using different stereochemical modes. Of course, if this had to follow a disrotatory mode of closure, let us write that one also. A disrotatory mode of closure. If it was disrotatory, obviously during disrotatory mode of closure, one lobe has to move in a clockwise direction. Let's say second lobe moved in a clockwise direction and the the seventh lobe moved in a anti-clockwise direction. It was one disrotatory mode. The second disrotatory mode was if, let's say, second lobe moved in an anti-clockwise direction and seventh lobe moved in a clockwise direction. Now what would have been the product? Again, the basic structure of the product would remain same. The only difference in the products will be where will the substituents on seventh and second carbon atom, that is this and this, go. So I can write the basic structure of the product. That is going to remain same, something like this. Here, 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 here. Right? Okay. Let's consider the first stereochemical mode in which second lobe moves in a clockwise fashion and seventh moves in an anti-clockwise fashion. Let's come back here. Second lobe moves in which direction? Clockwise. What is clockwise direction? Like this. If it moves like this, where will the methyl go? Methyl will go up. Okay. That means in this product here, when second lobe is moving in a clockwise direction, methyl goes up and correspondingly hydrogen will go down. Let's go back. If second is moving in a clockwise direction, since it is following a disrotatory mode of ring closure, the seventh lobe will move in an opposite direction, that is the anti-clockwise direction. Now considering the anti-clockwise direction, this seventh lobe will move like this. This seventh lobe will move like this. Once it moves like this, the substituent on seventh is here. This will go down the plane. If this goes down the plane, that means methyl will come here and hydrogen. That means methyl will come here and hydrogen will come here. That means the geometrical relationship between the two substituents on second and seventh carbon atom would be what? Trans. Similarly, the other disrotatory stereochemical mode is if this lobe in first case the second lobe was moving in a clockwise direction. In second case the second lobe will be moving in the anti-clockwise direction. What is that? Second here, anti-clockwise like this. If this is anti-clockwise, where will methyl go? Methyl is here, methyl will go down the plane. If this methyl goes down the plane, of course hydrogen would be above the plane. Similarly, if the second lobe is moving in an anti-clockwise direction following a disrotatory stereochemical mode ring closure, the seventh lobe would be moving in a clockwise direction. Seventh lobe moves in a clockwise direction means seventh lobe is moving like this. If seventh lobe is moving like this, the methyl will go above the plane. So hence your methyl would be going above the plane. Here hydrogen would be going below the plane, methyl above, hydrogen below. And what is the geometrical relationship between the two methyls at second and seventh carbon atom? Again, this is trans. So we have categorized 4 products here corresponding to the stereochemical modes of cycloaddition. These 4 products are 2 conrotatories, both lobes moving in clockwise or both lobes moving in an anti-clockwise direction. 2 disrotatories in which first lobe is moving, that is second lobe is moving in clockwise and seventh in anti-clockwise, and the second product is second in anti-clockwise and seventh in the clockwise direction. You can see the geometrical relationship of both conrotatory products remain same. The geometrical relationship of both disrotatory products remain same. How do I categorize this reaction? Since there were 6 pi electrons involved in electrocyclisation, I can call this electrocyclic reaction as 6 pi electrocyclisation reactions. Right? So this is something regarding a hexatriene system with different subsequents attached to it. Okay. Now I'll ask you a question. Try to work it out yourself. That I'll give you a reactant and then we'll give you a product. Then can you work out, following from the reactant and the product, which stereochemical mode is operative? Let's say here. Let's say example 2. I give you this thing. I have, let's say, a methyl here. A methyl here. This is my system. If it follows, let's say, a ring opening in such a way that it forms a hexatriene, methyl comes here, methyl comes here. Now can you, from just by looking at the reactant and the product, tell me which stereochemical mode is operative in this ring opening? But before you do that, one thing you need to understand is that while writing the product of electrocyclic ring opening, I need to open the bond. Which bond? That bond which is allylic to the double bond. This double bond, and this is the allylic carbon atom. This is the allylic bond. If this bond breaks like this, then we'll end up in the acyclic open chain system, something like this. The point is, where will these 2 methyls grow? It is going, one is going towards at this carbon atom. Let's say again, if this carbon atom is second, as I followed in the last example's nomenclature, if this carbon atom is second and methyl is below the plane, this carbon atom is 7th where methyl is above the plane. In the product, the methyl on the second carbon atom is going towards the right side and methyl on the 7th carbon atom is going towards the left side. What is the stereochemical mode operator? Now what do I need to do? While opening, as I've told you in the previous lecture, while opening a electrocyclic ring, what do I need to do? I need to put my thumbs in such a direction so as to show a bonding overlap between 7th and the second carbon atom like this. Now if this ring has to open up, this will open up like this. This is what I told you, it will open up like this. This is disrotatory and this is conrotatory. Disrotatory, conrotatory. I don't know what mode is operative. That can be adjudged only looking at the nature of the 2 methyls in the product. Okay, this methyl was below the plane. That means this was the sigma bond. This was the sigma bond between the 2. This methyl was below the plane, like here, as in here. Now this methyl is this opening up in such a way that this methyl here, which was below the plane, is going towards the right side. That means this lobe is opening like this. Try to understand this thing. This was the sigma bond here. The methyl was below the plane. Now methyl in the below the plane is going towards the right side like this. That means this lobe is moving in this direction. What is this direction? First lobe moving in an anti-clockwise fashion. That means the first lobe at the second carbon atom is moving in an anti-clockwise fashion so as to bring this methyl towards the right in the acyclic product. And then towards the second lobe of this 7th carbon atom, how this will put this methyl outside. Now in order to put this methyl outside, methyl is below the plane. Okay, try to understand that how do I put or how do I open up the ring system. Now second and seventh carbon atom was like this. The methyl on the second carbon atom is below the plane, methyl on the seventh carbon atom is above the plane. This is how this molecule in the cyclic form looks like. In the product, this methyl is going towards the left side and this methyl is going towards the, see, again towards the left side. This is how it opens up. That means both the lobes are opening up in this fashion. This methyl was below, this methyl was up. In order to put this methyl towards the left, I have to open up like this. In order to put this methyl towards the right, I have to open up like this. That means both lobes are moving like this. What is this motion? Consider this thumb. This is moving in an anti-clockwise fashion. What is this motion? This motion is again anti-clockwise. That means both lobes are moving in an anti-clockwise fashion. That means the stereochemical mode operative is conrotatory. You understand? And repeat again. While opening up a cyclic system, I have to consider my thumbs like this. How does it open up? There are two stereochemical modes. If it opens up like this, see, the first lobe in an anti-clockwise fashion, the second lobes in a clockwise fashion. This is like this. This is clockwise. This is anti-clockwise. Clockwise, anti-clockwise. So this is distrotatory. Distrotatory. Similarly, this would be distrotatory. So I have two distrotatory modes of ring opening, like this or like this. Fine. Now conrotatory. If this is, let's say, clockwise, this is also clockwise. So if this is the mode, both lobes are moving in a clockwise fashion. This is one conrotatory. Both in an anti-clockwise fashion, this is second conrotatory. So distrotatory, conrotatory, two modes. Right. Now let's again take this example. This is my product in which these are the two p lobes which are forming the sigma bond in a cyclic product. The methyl in the second carbon atom is below the plane. The methyl on the seventh carbon atom is above the plane, like this. Now I want to shift this methyl towards the left side and I want to shift this methyl towards the right side. In order to shift this methyl towards the left side, I need to move this p lobe like this. Now what is this mode? What is this motion? If it is moving like this, is anti-clockwise. So first lobe, that is the lobe on the second carbon atom, is moving in an anti-clockwise fashion. Okay, this methyl has to go towards the right. How will it go towards the right if this lobe moves like this? So that means this lobe is moving in an anti-clockwise fashion. So both are moving in an anti-clockwise fashion like this. And what was this stereochemical mode? Conrotatory. Hence, now considering the similar example in this particular way, let's say if the methyl is below the plane and this methyl is above the plane and this opens in a disrotatory manner, then where will these two methyl substituents go in the product? Or conversely, looking at the reactant and the product, what is the stereochemical mode operative? This is what we have to see. If you look at this particular example, you see this methyl is going towards the methyl on the second carbon atom is going towards the right. The methyl on the seventh carbon atom is also going towards the right. Now what is the mode? This is the sigma bond. Keep your hands like this. The methyl is below the plane. Since it is below the plane, this methyl below the plane, if this lobes move in this direction, or if you're not clear with this, let me draw it in this fashion also. This was the sigma bond which was formed between these two lobes. The methyl was below the plane. This methyl, let's say, is above the plane. This is how this molecule appears like. Now if this methyl is going to go below towards the right side, this lobe has to move in this direction, then only it will go towards the right side. That means like this. And similarly, if this methyl has to come here in your acyclic product, then how will this lobe move? This methyl has to come here, and probably this lobe would move in this direction. Now what is, sorry, in the product, again I'm showing the wrong way. In the product, this methyl is towards the right side, not towards the left side. If this has to come towards the right side, that means this lobe has to move in this direction. Now since this lobe are moving, this, if you can find, this mode of motion is anti-clockwise, this is clockwise, that means both lobes are moving in opposite direction, hence this is a disrotatory mode of ring opening. Right? Let's take one more example. This will substantiate our point here. Okay, example 3. Let's take the example of an octatetraene, this molecule. Let's say we have a double bond here, we have a double bond here, we have a double bond here, right? So this is what a double bond at this position. So this is what my octa, cyclo-octa 1,3,5 triene molecule. Let's say if this opens up in a disrotatory, conrotatory manner, then what would be the product? In order to understand this thing, I need to focus on this thing, that which bond is opening. Now remember, we are opening up a electrocyclic ring to a acyclic product. This is the 3 double bonds attached to the first carbon atom. Here is this 7-8 bond, which is allylic. That means this bond has to open. In order, or in a method of drawing the arrows, in order to open up the chain, I need to open up the bond which is allylic to the double bond of the double bond of the the terminal double bond of the polyene system. This is the polyene system. Terminal double bond is either at 1 position or at 5 position. This terminal double bond at 1 position have 7-8 bond allylic to it. Similarly, double bond at 5 and 6 position has the 7-8 bond allylic to it. That means this bond has to break. This breaks, this double bond will come here, this will move in this direction, this will move in this direction, this will move in this direction, and I'll end up in the formation of what? An octatetraene system in a cyclic form like this. So it is 8, 1, 2, 3, 4, 5, 6 and 7. Now 7-8 single bond becomes 6-7 double, 5-6 double bond becomes 4-5, 3-4 becomes 1-2, and this is my cyclooctatetraene molecule. I have 2 hydrogens here. Where will this hydrogen go in the product? This is what I want to see. This is my conrotatory. Where will this hydrogen go? This is the acyclic product. Now considering this acyclic product in a conrotatory fashion, I cannot say where will these 2 hydrogens go, because here at 7 and 8 position both are hydrogen, and since both are hydrogens in nature, this hydrogen can occupy either of the positions. So I can simply write my product in this way. So either it is conrotatory or disrotatory, the product formation would be similar. The differentiation can only be had once you have different substitutions at these 2 allylic carbon atoms, that is 7th and 8th carbon atom. Okay, let's look at this example in a different perspective. Similar example, let's say example 3. Let's put it this way. Similar example, let's take this cyclooctatetraene system and draw it in a similar way. Let's say if this molecule has to cyclize, not just open up, cyclize in such a way that my product is this one. Can I figure out what kind of a reaction am I talking about? And if it is electrocyclic reaction, what kind of electrocyclic reaction I am talking about? Now in order to understand this thing, consider the reactant and the product, and consider it in lines with electrocyclic reaction. This is a conjugated polyene system. It has 3 pi bonds. It's a cyclic system. The product is a bicyclic system. That means from a cyclic system to a bicyclic system. That means one cyclic chain has increased, right? In this reactant, I have 6 pi electrons. In the product, the number of pi electrons are now, because it is 2 pi bonds, are 4 pi electrons. And what has happened? A new sigma bond is formed. 1 sigma bond. So this can fit into the category of electrocyclisation reaction. Then first point, that this is electrocyclic reaction. Then what is the category of this electrocyclic reaction? Remember, the electrocyclic reactions are categorized on the basis of the acyclic component or on the basis of the reactant which is cyclizing. Since it is not acyclic, but this is the reactant which is a cyclic system and it is cyclizing into a bicyclic system, in this reactant I have 6 pi electrons. That's why I should call this reaction as a 6 pi electrocyclisation reaction. Okay, how Then the third point, how did this reactant got converted into this product? In order to understand this thing, I only need to figure out or focus at the position of the double bonds. Where are the double bonds present here? The double bonds, the terminal position of the polyene system is first carbon atom and sixth carbon atom. This is the polyene system. If it has to cyclize, it is the terminal carbon atoms of the polyene system it cyclizes. That means this 1,2 bond should become 1 and 6. 6, 5 will become 5 or 6 will become 4 and 5. 3 and 4 will become 3 and this thing. So I would end up in this kind of a cyclic product. Let's retain the numbering 1, 2, 3, 4, 5, 6, 7 and 8. Right? And if I simplify this product, this is what 1, 2, 3, 4, 5, 6 a 6 membered ring. Can be written this. This is what a 4 membered ring, like this. This is the first carbon atom, second, third, fourth, fifth, sixth, seventh and eighth. Between 2 and 3 there is a double bond. Between 4 and 5 there is a double bond. Right, this is the product. Now, if you look at the reactant, here, you'd find that both hydrogens are having a trans relationship with one another. Now, how will they have a trans relationship with one another will be decided on the basis of stereochemical mode, and that is where we'll explain that what stereochemical mode is followed. Now, which hydrogens are we talking about? If you look here, or if you look at the product, hydrogen 1 and 6 are the points of consideration. In the reactant, there are 1 and 6 hydrogen atom. The first hydrogen atom should be here, and the sixth hydrogen atom should be here, in order to have a 120-degree bond angle of the first carbon atom, sp2 hybridized, and 120-degree bond angle of the sixth carbon atom, right? The hydrogen should be drawn in this fashion. Now, in the product, this hydrogen is going above the plane, and this hydrogen is going below the plane. Now, consider this as an acyclic system, because this flap is not participating, the 7/8 carbon atoms are not participating. You have a p lobe here, and hydrogen is here. Now where will now this has to cyclize. How it is cyclizing? If this lobe moves in this direction, now where will the hydrogen go? Hydrogen was here, hydrogen will go above the plane. This lobe, hydrogen is here. Where is the hydrogen going? Below the plane. That means this lobe is moving in this direction. Again, this was the p lobe of the sixth carbon atom. This is the hydrogen. Where is the hydrogen going? Below the plane. That means this lobe is moving in this direction. So the lobe on the first carbon atom is moving in this direction. The lobe on the sixth carbon atom is moving in this direction. That means both lobes are moving in an anti-clockwise fashion in the same direction. Hence, the stereochemical mode operator is conrotatory, and this is the stereochemistry of the product form. Had been the product this one, let's see, following a disrotatory mode, what would have happened? Similar kind of product. The only difference is that where would have these hydrogens gone, right? Were both the hydrogens above the plane or both the hydrogens below the plane? Till now, considering the examples we have dealt with, you can very well imagine that if the product of the conrotatory ring closure is trans with respect to hydrogens at first and sixth carbon atom, the product of the disrotatory should be cis, either both hydrogens above or both hydrogens down. Now, in order to understand this product, disrotatory means the lobe at first carbon atom and the lobe at the sixth carbon atom should move in opposite direction. If the lobe at the first carbon atom is moving, in a, let's say, as in the product, as we've written in the product, this hydrogen we are showing above. If the lobe in the first carbon atom is moving, let's say, in this direction, hydrogen will go up. If the lobe on the sixth carbon atom is moving in this direction, hydrogen will go up. This is what an anti-clockwise motion, this is what a clockwise motion, and since these are moving in opposite directions, disrotatory mode will push both the hydrogens towards the above side. That means if these two hydrogens have a trans relationship with one another, the disrotatory mode will have both hydrogens in a cis geometrical relationship with one another, right? So what is the category of electrocyclic reaction? What is the stereochemical modes operative, and which component is an acyclic component? See, earlier in the examples we've only dealt with acyclic systems going on to form a monocyclic product. Electrocyclic reactions can be also in which a monocyclic system can form a bicyclic product, or a bicyclic system can increase on one cyclic ring and become a tricyclic. So in general, electrocyclic reactions should add on one ring to the framework of the acyclic system or to the framework of the reactants. Right. We talk about another example here, or you can call it as the C category, that is electrocyclic reaction. We have done electrocyclizations in 4n components, in 4n plus 2 pi component. We'll talk about electrocyclization in allyl systems or allyl carbocations. You know what is an allyl carbocation? You should have this kind of a system, allyl, or you can also call it as propenyl carbocation. If I have this kind of a system, this kind of a systems are acyclic to start with. They can cyclize in a similar fashion as in all electrocyclic reaction. Let's say this one. Again, this can cyclize in such a way that this double bond moves here, and this results in the formation of a cyclic 3-member ring with a positive charge is now carried on to this. Of course, the mechanism of the action of this reaction is simple. These two carbon atoms are sp2 hybridized because they are double bonded. Carbocation, as we know, is sp2 hybridized. So if I draw the orbital picture, I would have drawn it like this, where the two p lobes forming the pi bond and the p lobe holding the positive charged carbocation are parallel to one another. Again, all we need to do is we need to move this. This is one electron, this is no electron. All we need to do is we need to move this electrons to this fashion. If this bond or this lobe moves in this direction, this lobe moves in this direction, we'll end up in the formation of a cyclic system. That means an allyl carbocation will be formed, and this is what a 3-membered cyclic system having a positive charge. The rules of the cycloaddition, the rules of the motion would remain same. These two lobes can either move in the same direction, both clockwise, both anti-clockwise. These two lobes, this would be commutatory. If one lobe is moving in a clockwise direction, other in an anti-clockwise, or this one in an anti-clockwise, this one in a clockwise fashion, then probably this is the disrotatory stereochemical mode of electrocyclization reactions. This we have already talked about in the examples we have. Right. Now we'll talk about another example, a bit complicated than the previous one. Let's say this one. Can we explain? Okay, we'll talk about an example. Can we explain that what is the stereochemical mode operative in this system? Octatetraene system. One methyl, let's say, is here, one methyl is here. Of course, hydrogen will be here and here. I've not properly drawn. This hydrogen should have been drawn like this. This hydrogen should have been drawn like this inside because it appears to be puckered. I have not drawn it. Let's say it is cyclizing in a commutatory manner. You can see this double bond in which both methyls are on the similar side is having on this methyl, this larger group, and this methyl are on the same side. Should be this one hydrogen, and this hydrogen and this hydrogen are opposite. That means this is trans. That means this is having a let me correctly put it because this is not shown in the right fashion. Let me show it properly. Methyl here and hydrogen here, maintaining a 120 degree bond angle. Okay, methyl here and this hydrogen here. This is the right way of drawing this molecule, so that we can show that this carbon atom is having a 120 degree bond angle with one another, right? If this is undergoing electrocyclic ring motion in a commutatory fashion, this is what we want to discuss, right? How many pi electron system is the acyclic component? 4 pi bonds, 8 pi electron system. How will it cyclize? Again, we have to move the terminal. These are the terminal carbon atoms of the polyene system, as you can see. That means there should be a bond formation between first and the 8th carbon atom. This lobe will move here, this will move here, this will move here, this will move here. This we know. The result is the formation of, from a octatetraene system, I'll end up in a cyclooctatetraene system where first and the 8th carbon atom will become sp3 hybridized. That means tetrahedral in nature. Okay, in the product, where are the methyls going? If the mode is quadrotatory, where are the methyls going? This is what we want to see. If it is quadrotatory, the p lobe on first carbon atom and the p lobe on the 8th carbon atom are moving in the same direction. Both can move clockwise. If both moves clockwise, the methyl will here. If it is moving in a clockwise direction, methyl will go down, hydrogen will go up. If methyl is here, this is moving in a clockwise direction, hydrogen is towards the inside, methyl is towards the left side, then methyl will go up. That means this methyl will go up and hydrogen will go down. So if this is moving in this direction, let's say both are moving in a quantitative fashion in a clockwise manner, this methyl would go down and this methyl will go up. Similarly, the second product would be when both lobes are moving in an anti-clockwise fashion, and you can write the product similarly. It will be opposite to what we have got here. That means if here hydrogen was at the first and 8th carbon atom, if hydrogen was below, here hydrogen will be below and methyl will be up, and here hydrogen will be up and methyl will be below. You can follow this up anti-clockwise here like this. Anti-clockwise, methyl goes up. Anti-clockwise, here the hydrogen is down, methyl will go down. Hence this is the quantitative ring opening ring crochet product of the 4 and pi systems having 8 pi electrons. Again, this is an 8 pi electrocyclisation reaction. Okay, I'll focus your example and try to work out that what will be the product of this electrocyclic reactions. This will be the last example of electrocyclisation which we'll be discussing. I have an example which, let's say I have an octatetraene system like this. There are 4 pi bonds, of course, like here. Here I have, let's say, this reactant, and here I have this reactant on this side. This went on under thermal conditions. Forget about the reaction conditions because we will be dealing this with in the later part of the chapter. This electrocyclized and formed this product, this one. Hydrogen here, hydrogen here. Acid functionality. This is above the plane. Above the plane. And this product. Can we account for the formation of the products which we have lifted here? Which this hydrogen is below the plane and this hydrogen is below the plane. Can we account for the formation of these two products from this product? Now, in order to understand this thing, we have to first of all consider what kind of electrocyclic reactions are we talking about. What kind of electrocyclization we are talking about here? This is an 8 pi system having 4 pi bonds and 8 pi system. How will this lead to the formation of this product? We have to see, and then we'll talk about the stereochemical part, which would be followed from the stereochemical mode in the reaction. Right, let's go step by step. Let me call this system as A reactant, let me call this as B reactant. Okay, so in order to simplify this thing, again I'll draw cyclooctatetraene. Reactant A here, reactant B here. Substituent A here and substituent B here. This is it. If this undergoes a reaction in such a way that in the product, if you consider where is the substituent A and substituent B going in the product, A going below the plane, B going above the plane in both the products, A going below the plane, B going above the plane. That means this ring, if it cyclizes, it will have, how it will cyclize? First of all, it's an 8 pi electron system. Since it's an 8 pi electron system, this will cyclize in this fashion. If it cyclizes in this fashion, you'll have this molecule 1, 2, 3, and let me number this 1, 2, 3, 4, 5, 6, 7, and 8. At 1 and 8th carbon atom, you'd have a tetrahedral configuration in which B in the product is going above the plane and A is going below the plane. That means this B should be above the plane and A should be below the plane in the product. Now this has to follow only once there is a particular stereochemical mode of this ring closure. Now let's see. B going above the plane. If this is the P lobe here, how would B go above the plane? B is here, B would go above the plane only if this ring closes like this, and A would go below the plane only if this ring closes like this. Again, B is here, B will go above the plane if this ring closes like this. A is here, A would go below the plane if this ring closes like this. Hence both the lobes, A moving in anti-clockwise fashion, P and the lobe on the first carbon atom is moving in an anti-clockwise fashion, the lobe of the 8th carbon atom is moving in an anti-clockwise fashion. So both lobes are moving in an anti-clockwise fashion to make this product. This is a conrotatory ring closure. That means the first thing which we have understood is the first electrocyclic reaction, which is an 8-pi electrocyclisation in a conrotatory fashion of a octatetraene system leading to the formation of cycloocta 135 triene framework. Right, this is one thing. Now you can see that the product is not the product which we have desired, is not this one, but it is this one. This is not the product we have desired, this is the product we have desired. That means this 6 pi electron, and you can see here obviously that this had 6 pi electrons, this has 4 pi electrons, 2 pi bonds, it has 3 pi bonds, it has 2 pi bonds, as you can see. Now since it has 3 pi bonds, this has 2 pi bonds, it has 1 sigma bond more. That means one can consider this molecule is further electrocyclizing into this. And if this is electrocyclizing into this, what were the carbon atoms here? The carbon atom 2nd and 7th are the terminal ends of the 6 pi electron polyene system, hexatriene system. That means 2nd and 7th carbon atom has to cyclize. Again, how do they cyclize? There should be a bond formation between 2 and 7. 2 should come here, 6, 7 should go to 5 and 6 again, and 4, 5 should go between 1 and 2. That means this will lead to the formation of this kind of a product, right? See. An 8-member ring. Again I'll number in order to simplify the case. This is 2, 3, 4, 5, 6, 7 and 8. At the first carbon atom, this B substituent, that was your polyene system, is above the plane. Here the A is below the plane. A is below the plane. And the bond is formed between the 2nd and 7th carbon atom. 2, 3 double bond goes to 3 and 4. 4, 5 double bond goes to 5 and 6. If I simplify and write this product, I can write it in this fashion. This is what? 1, 2, 3, 4, 5, 6 member ring. And then between 2 and this is 2, 3, 4, 5, 6 and 7, right? Between 2 and 7 there are 4 carbon atoms. That means it's a 4-member ring. 2 is attached to 1, 1 is attached to 8. 1 has this A substituent, this B substituent above the plane, 8th had this A substituent below the plane, and you have a double bond at 5 and 6, you have a double bond. So we have constructed the framework of the product which we desired. And what is this electrocyclisation? A cyclic component cyclizing into a bicyclic component. So this is the reactant, the open chain component, this is the cyclized product. This had 6 pi electrons. Since the open chain component or the reactant had 6 pi electrons, I will call this as 6 pi electrocyclisation reaction. So I can say that this molecule is undergoing, the reactant is undergoing 2 consecutive electrocyclizations, one in 8 pi electrocyclisation constructing a cyclooctatriene molecule, then undergoing a 6 pi electrocyclisation constructing a bicyclic 6-4 system. A 6-4 system. Okay, now one thing is still left in this product. You see the carbon atoms, the hydrogens, if I had to retain this numbering, the hydrogen at 2nd and 7th carbon atom of the reactant are either going above the plane or they are going below the plane. What were 2nd and 7th carbon atom? Let's look at the reactant. This one. What were 2nd and 7th carbon atom? This one. in the reactant. Now if this hydrogen is going, either both are going above the plane, how will both these hydrogens go above the plane? See how I've drawn these hydrogens in order to maintain that 120 degrees bond angle of this sp2 hybridized second carbon atom, and similarly in order to maintain the 120 degree bond angle. Now if this hydrogen at the second carbon atom has to go above the plane, then this hydrogen is here, let's say above the plane only possible if this rotates in this fashion. What is this? Anti-clockwise. And this seventh carbon atom here, hydrogen was here, this will hydrogen will go above the plane if this rotates in this direction, so it's a clockwise motion. Second anti-clockwise, seventh clockwise. Remember what was this? A disrotatory mode motion, this one. So that means both hydrogen will move in a disrotatory motion in order to construct, in order to bring these two hydrogens in second and seventh carbon atom above the plane. And similarly, if both hydrogens are moving, or both lobes in the second and the seventh carbon atom are moving in the opposite direction, that is, if first lobe is moving in a clockwise fashion at the second carbon atom, and the seventh carbon atom's lobe is moving in an anti-clockwise fashion. What I'm saying, let's say first lobe here, hydrogen is here. If this lobe moves in a clockwise fashion, this will go down. If this moves in an anti-clockwise fashion, hydrogen will go down. So hydrogens at second and seventh carbon atom can go down. That means we have worked out that the stereochemical mode operative in this particular reaction is disrotatory. Hence, the overall reaction, if I have to explain this thing, is two consecutive electrocyclisation reactions. The first reaction is the condotatory 8-pi electrocyclisation of octatetraene to cycloocta 135-triene, followed by a disrotatory 6-pi electrocyclisation of cyclooctatriene to a bicyclic 6,4 product, where both hydrogens are going either above the plane or below the plane in the product. Take a pause, do this example yourself, and then we'll discuss that what kind of a reaction are we talking about. So with this, probably we will end up in explaining what are electrocyclic reactions. If I have to sum up, I'll say we've discussed what are electrocyclic reactions, in which an acyclic component cyclizes with the help of the pi electrons, k pi electrons of the reactant cyclizes to k minus 2 pi electrons of the product with a new sigma bond is formed. The reactions are reversible in nature. That means electrocyclisation can occur or electrocyclic ring opening can occur. The reactions are categorized on the basis of the number of pi electrons in the acyclic or the reactant. And then there are two possible stereochemical modes. The terminal p lobes of the polyene system can either move in the clockwise fashion, both the lobes, or both lobes can move in an anti-clockwise fashion. We call this stereochemical mode as condotatory. If one lobe is moving in a clockwise fashion and the other lobe is moving in an opposite anti-clockwise fashion, or vice versa, we call this stereochemical mode as disrotatory. Now, disrotatory and condotatory mode closures will bring about different products depending upon the stereochemistry, depending upon the subsequent attachment in the reactant. It can be either cis geometry or trans geometry, depending upon again the position of the subsequents in the polyene system. So with this, we are ending electrocyclic reactions. In next lecture, we'll be talking about the sigmatropic, that is the third category of pericyclic reactions. Thank you.